Drop a steel bolt into a glass of water. Gone. Instantly. It hits the bottom before you even process what happened. Now take that same steel, millions of those same bolts welded together into a structure 20 stories tall and nearly 4 football fields long, and set it on the open Atlantic Ocean. It floats. Not just floats. It carries 6,000 people, an ice skating rink, multiple swimming pools, real trees, and a full hospital. It crosses oceans in winter. It sails through 12-meter swells, without the passengers spilling their drinks. Every instinct you have says that is impossible. And if you only understand half the engineering, you are right to be confused. Today we are going underneath the waterline, into the systems running silently 24 hours a day that most passengers never know exist. By the end of this, the way you see any floating object will never be quite the same. Most people assume a ship floats because engineers made it light enough. That is not what is happening. A fully loaded, large cruise ship displaces somewhere between 50,000 and over 100,000 metric tons of seawater, the actual physical weight pressing down on the ocean. The largest ships afloat today are the equivalent of stacking nearly 300 fully loaded Boeing 747s on the surface of the water. Every day at sea, the engines burn through around 1,000 metric tons of fuel alone. This is one of the heaviest moving objects human beings have ever built. So why does weight matter less than you think? Here is the physics. When any object enters water, it shoves water out of the way. That displaced water pushes back, upward, with a force equal to the weight of the water moved. Archimedes worked this out 2,000 years ago, and it is still the foundation of every ship ever built, the principle of buoyancy. The hull of a cruise ship is not a solid block of steel. It is an enormous hollow shell. When it sits in the ocean, it displaces the entire volume of water that would otherwise fill that space. The cabins, the corridors, the restaurants, the engine rooms, all of it. The upward force generated by all that displaced water matches the downward pull on the ship. When those two forces reach equilibrium, the ship stops sinking. Not because it ran out of weight, because the ocean is pushing back just as hard as gravity is pulling down. That balance point is the waterline. Naval architects calculate this so precisely they can predict where the waterline will sit within centimeters before a single passenger boards. The hull geometry, wide, curved, deep, is designed to maximize displaced volume while staying strong enough for open ocean. Steel sections are prefabricated in pieces, sometimes as large as a suburban house, then assembled in dry dock like a three-dimensional puzzle. Floating is solved, but it is only the beginning of the problem. A hull that floats but rolls onto its side the moment a wave hits it is useless. Stability is a completely separate engineering challenge, and it comes down to one thing, where the mass lives inside the structure. A pencil balanced on its tip-tips at the slightest force. A weighted buoy pushed sideways, snaps back. The weight at the bottom creates a restoring force more powerful than whatever pushed it. A cruise ship is engineered to behave like the buoy. The heaviest systems, engines, fuel tanks, mechanical infrastructure, sit as low in the hull as possible. But the most important tool is ballast water. Large tanks, built into the very bottom of the hull, near the keel, are deliberately flooded with seawater. Not accidentally, on purpose, and in carefully calculated volumes. A large cruise ship carries tens of thousands of tons of seawater ballast on a typical voyage. That mass at the bottom drags the ship's center of gravity as low as physics allows. Naval architects call the resulting measurement metacentric height, the distance between the ship's center of gravity and the point where buoyancy force acts on the hull. The greater that distance, the more powerful the righting force when the ship tilts. Push it sideways, the low center of gravity pushes back. No active intervention required. And the ballast load isn't set at departure and forgotten. The ship's weight distribution changes constantly. Fuel burns off, passengers redistribute, water tanks empty. The ballast control system compensates continuously, pumping seawater between tanks across the lower hull around the clock. Most modern cruise ships also carry active stabilizer fins, hydrofoil blades extending from either side of the hull below the waterline, working like small wings. As the ship moves forward, the fins counteract a developing roll before it builds momentum. Gyroscopic sensors detect the beginning of a tilt, and the system adjusts within fractions of a second. On a winter Atlantic crossing, active fins can reduce visible rolling by more than 70%. The ballast system uses the ocean as a counterweight against itself. The same water trying to tip the vessel is being held inside it at the lowest possible point to resist that tipping. same substance. The engineering simply decides where each portion goes. Here's the part most people never hear. Water does not wait for a catastrophe to get inside a ship. It is already in there, on every vessel at sea tonight. This is not an accident. It is an anticipated, designed reality, managed continuously on every single voyage. The propeller shafts must exit the hull below the waterline. There is no way around that. The shaft seals are engineered precisely, but they work in a constantly flexing environment and allow a controlled amount of water past them at all times, by design. Every pipe that penetrates the hull for cooling systems, ballast lines, and fire suppression is another managed entry point, a deliberate hole in the bottom of the ship. Water also enters as condensation. Cold steel hull plates, next to warm, humid air from running machinery, deposit moisture against every surface continuously, like a cold glass sweating on a warm afternoon. Except it is happening across thousands of square meters of steel around the clock. Wave action sends spray into ventilation openings. Rain penetrates deck fittings. The hull flexes microscopically in heavy swells, working every seal with every passing wave. None of this triggers an alarm. It is all managed by the bilge system. The bilge is the lowest interior space of the hull, drainage channels and collection sumps running along the very bottom, below everything. Gravity does the work. Every drop of water that enters the ship travels downward until it reaches the bilge. Pumps move it out through discharge lines and return it to the ocean. On a large cruise ship, this is not one pump in a corner. It is a fully distributed network of independent pumping stations throughout the vessel. If one fails, the others continue. The system runs in port, in calm water, during storms, silently at 3 in the morning, while 5,000 people sleep with no idea. Most passengers spend an entire week aboard and go home without ever thinking about the continuous, invisible process running directly below their feet. It is the actual reason they stayed dry. Everything so far assumes the hull stays intact, but the ocean is patient, and the engineers know that. So they did not design a ship that keeps water out. They designed a ship that survives water getting in. It is a fundamentally different problem, and the solution is one of the most elegant ideas in the history of naval engineering. Every large cruise ship is divided internally into dozens of watertight compartments, sealed sections of the lower hull that cannot communicate with each other unless a valve is deliberately opened. Think of it as a sealed egg carton sitting on the water. If one cell floods, the walls hold. The flooding stops at a boundary. Adjacent cells stay dry. The ship loses buoyancy in that one zone, but retains the lift of every other compartment still full of air. This is compartmentalization. The technical measure of how much flooding a ship can absorb is called its damage stability rating. Modern cruise ships are designed to survive 2 or more adjacent compartments flooding simultaneously without sinking. Some current vessels can absorb significantly more before the equation tips past recovery. The watertight doors sealing these sections are not the panels passengers walk through at dinner. They are thick, hydraulically operated panels set into reinforced steel frames, built to hold back the full pressure of a flooded compartment on one side, while the other side stays completely dry. They are monitored from the bridge and can be closed remotely in under 30 seconds. The entire lower hull can be sealed before most passengers on the upper decks register that anything has changed. All of it is monitored from the ship's integrated bridge system, hull sensors, ballast tank levels, bilge pump activity, watertight door positions, stabilizer fin angles, list and trim readings, all live. If the ship develops an unexpected lean overnight, the system flags it and compensates automatically. If a bilge pump starts working harder than normal, it shows up on a display. The ship is not just engineered to handle the ocean. It is continuously watching itself, cross-checking its own systems, and correcting in real time. So here's where all of this lands. A cruise ship floats because its hollow hull displaces more ocean weight than it contains. It stays upright because its mass is deliberately concentrated at the lowest possible point, using tens of thousands of tons of seawater as ballast to generate a righting force powerful enough to push back against whatever the ocean sends. It handles the water that enters constantly on every voyage through a bilge network, running silently below every passenger deck. It survives serious flooding because the lower hull is divided into sealed compartments that stop any intrusion from spreading far enough to matter. The ocean is not the enemy of a cruise ship. It is the working material. The ship floats in it, ballasts against it, drains it back out, compartmentalizes against it. Every major system is either using the ocean or managing it. The engineering does not fight the water. It decides where each portion goes. That is what this much steel actually is when you look underneath it. Not a boat, not a floating hotel, a continuously self-correcting machine. reading the ocean in real time, using the ocean's own weight to stay alive. Next time you watch one of these things move, look at the water line. That thin line between steel and sea is where every system in this video is happening simultaneously, invisibly, without pause. That line is the whole story. If this is the kind of engineering that stops you mid-scroll, you're in the right place. We break down the hidden systems behind the things that move the world: ships, bridges, tunnels, and infrastructure most people use every day and never once question. Subscribe so you don't miss what's coming next. Every video goes deeper than the last. See you on the next one.